welcome back to mass transfer operations 2 course, and we are discussing on drying operations. In the previous class we discussed on the rate of drying for batch dryers. In that section we discussed on the cross circulation drying and through circulation drying. Now we will be discussing on the rate of drying for the continuous dryers. There are so many continuous dryers available in the actual applications. The most widely used continuous dryer is the rotary dryer. From one side of this rotary dryer, this wet solid enters, and from the opposite side the hot air enters as the drying medium. So, in most of the cases the continuous dryers are of counter current mode. So, we will be discussing on the rate of drying for the continuous counter current dryers. So, for that we need to do some material and energy balance, and that will be like this, that is integral part of the design calculation of all kinds of dryers including the continuous dryers. So, first of all we will be taking this dryer like this. So, there say solid wet solid will be entering from here like this, we can say moist solid enters, that is we can say, let us take this flow rate is Ls, and say moisture content is, say we can say x1. We take this one, that where this moist solid enters, that is we can say this is a cold side as the station 1, and where the dry solid will be exiting, that is we can say this station 2. And now we say the temperature of the solid is like this Ts1, and enthalpy will be Hs1 prime. And whenever this dry solid will be exiting like this from here, we will say that a dry solid with this flow rate will be Ls, that is dry basis, and then moisture content will be x2, that is definitely lower than x1, and the temperature will be Ts2, that is definitely greater than Ts1, and the enthalpy value Hs2 prime. And I told that this most of the continuous dryers operate in the counter current mode. So, we say this drying gas will be entering with this Gs flow rate, with this humidity is say Y2, and temperature will be say Tg2, and enthalpy will be Hg2 prime. Whenever it will be leaving this dryer, so that time we can say this one flow rate will be like this, flow rate of the gas will be Gs, and then humidity will be Y1. That humidity will be definitely greater than this Y2, and temperature will be say Tg1, and enthalpy will be Hg1 prime. This one we can say this one apply this some say heat will be applied here, and some amount of the heat will be lost during this counter current operation. That amount we can say this one Q prime, that is we can say this one rate of heat loss. So, we can say this one Q1 prime is the rate of heat loss. Okay. So, here Ls is this, we can say this one flow rate of the moist solid. Then a dry basis, x1 is this moisture content, and Ts1 is the temperature of the solid at the entry, and x2 is the moisture content of the dry solid, that is we can say this one which one is the desired one, and Ts2 will be the temperature of the dry solid. Okay. And Y2 will be this humidity of this drying medium, and Y1 will be the humidity of the drying medium when it is exiting from the dryer. So, it is we can say this one continuous dryer. Now, we need to do the moisture balance first. So, we will be doing this moisture balance. Across the dryer, that will be say Ls into x 1 plus Gs into y 2 is equal to Gs into y 1 plus Ls into x 2. So, from here we can say this one just by manipulation we can say Ls into x 1 minus x 2 is equal to Gs into y 1 minus y 2. And whenever we will be doing the enthalpy balance, we need to consider the entire dryer. So, for that we have this Gs into Hg 2 prime plus Ls into Hs 1 prime is equal to Gs into Hg 1 prime plus Ls into Hs 2 prime plus that q prime which is lost. Okay. We have to take this T 0 as the we can say this one reference temperature. Then we need to calculate this Hs prime values like this from the specific heat values, that is we can say this one Hs prime is equal to say Cps into Ts minus T 0 plus x into Cpl into Ts minus T 0. Okay. So, that is nothing but we can say this one we will say is equal to Cps into Ts minus T 0 plus 4.187 into x into Ts minus T 0, where we can say this one the Cps, that is the specific heat of solid, then Cpl is equal to a specific heat of liquid, here it is water, that is we have taken as this 4.187 kilojoule per kg Kelvin, and we will be calculating this enthalpy of the gas, that is we have say taken this one as the solid. So, we will be calculating this enthalpy of gas, say enthalpy of gas, say this Hg prime, that is equal to Cpg into Tg minus T 0 plus y into Cpv into Tg minus T 0 plus y into lambda w. So, here this Cpg is equal to say 1.005 into Tg minus T 0 plus Cpv is equal to say 1.88 into y into Tg minus T 0 plus y into lambda means y into 2500. So, here we can say this lambda w, that is we can say this on latent heat of evaporation of water at this reference temperature T 0 means at 0 degrees Celsius or 273 Kelvin, and this Cpv actually is the specific heat of vapor. This Cpv is the specific heat of water vapor. That is we can say that is equal to say 1.88 kilojoule per kg Kelvin. Okay. So, now actually we will be solving one problem on the say continuous dryer. So the problem is very simple, like this: a non-hygroscopic filter cake is to be dried in a continuous counter current dryer from 30% moisture to 2% moisture, that is wet basis, at a rate of say 1000 kg per hour. The material enters the dryer at 27 degrees Celsius and leaves at 52 degrees Celsius. Fresh air is mixed with part of moist air leaving the dryer and heated to a temperature of 120 degrees Celsius in a finned air heater using low pressure steam, that is say 4 kg per centimeter square gauge. Now, we need to calculate the rate of flow of fresh air that is required to dry this wet solid, and the fraction of the air leaving the dryer that is recycled, then the theoretical steam requirement and the heat loss from the dryer if there is any. Now, the data which are given to solve this problem are like: temperature of the fresh air is 29 degrees Celsius with the humidity is 0.018 kg per kg dry air, and humidity of the air leaving the heater is 0.03 kg per kg dry air, and humidity and temperature of the air leaving the dryer is 0.05 kg per kg dry air, and temperature is 70 degrees Celsius. Specific heat of the dry solid is 920 joule per kg Kelvin, and latent heat of the steam at this 4 kg per centimeter square gauge pressure is 2110 kilojoule per kg. Now, we need to solve this one. It is simply we can say this counter current dryer and continuous one. Okay. So, first of all we need to draw this diagram. We can say this one, we take this one just like we will take first the basis, as this we can say 1 hour. Let us take this for simplicity, and we need to draw this total flow sheet diagram for this problem. Like this, we have this dryer, and say one heater is there before this dryer. So, it heats the drying medium prior to the entry of this dryer like this, and it leaves the dryer, and then a part actually is recycled. A part of this, we can say this one drying gas actually is recycled back to this heater. Okay. So, we need to get this one, and the solid is entering from here, and so we will take this one, that the flow rate of the solid is Ls, and temperature of this solid will be Ts1, and this we can say this Tsi also we can take. Then the humidity, this moisture content is Xi, and enthalpy is say Hsi prime. And whenever it will be leaving the dryer, so this flow rate will be say, let us take this flow rate will be this Ls, there is a dry basis, and this temperature will be say Ts out. So, Ts out, and say the moisture content will be X0 and enthalpy will be Hs out prime, and this heater actually takes this QH amount of heat to heat this we can say drying medium, and whenever it will be entering the dryer, say we can say flow rate will be like this. Flow rate of this hot air will be Gs2, and temperature will be say Tg2, and humidity will be say Y2, and enthalpy will be Hg2 prime. And whenever it will be leaving this dryer, this hot air will be leaving, then we can say this one, the flow rate will be say this Gs3, and say we can say this one again, it will be same as GS2, and say, and humidity will be, we can say this one Y3, and say enthalpy value will be Hg3 prime, and one part actually will be leaving. So, that will we can say this one at say GS1. Let us take this one with this Y3 will be same, and Tg3 will be same also, and we can say this Hg3 also will be same. So, only one part, say out of this one part actually is recycled. So, this part actually we can say this flow rate will be like this, total flow rate is GS3 minus this GS1, GS3 minus GS1, and say, and humidity will be say H3 Y3, and enthalpy will be Hg3 prime. Okay. So, this is the, we can say this one the schematic diagram of the, we can say this one dryer. So, this is the important part of the to solve a problem, schematic diagram, continuous dryer. Okay. So, now whatever the conditions are given to solve the problem, we will be now noting down, like this temperature of the fresh air, I told this one at 29 degree Celsius, then humidity is 0.018 kg per kg dry air, then humidity of the air leaving the heater is 0.03 kg per kg dry air, humidity and temperature of the air leaving the dryer is 0.05 kg per kg dry air and 70 degree Celsius, specific heat of the dry solid, that is 920 joule per kg Kelvin, and latent heat of the steam at 4 kg per centimeter square gauge pressure, this one is 2110 kilojoule per kg. Okay. So, now from there actually we will be calculating this one step by step, we will be doing this one. Let us take, we have Tg1. So, we have Tg1, that is equal to 29 degree Celsius, and Y1 is equal to 0.018. Now, we can calculate the what will be the enthalpy value at Hg1 prime. So, that we will be calculating just using this simple formula, Hg1 prime is equal to say 1.005 plus 1.88 into y prime 0.018 into Tg1, that is you can say this 29 minus reference temperature is equal to 0 plus 2500 into y1, that is 0.018. So, this is coming out to be as the 75.13 kilojoule per kg. Okay. So, then we need to calculate the Hg2 prime. For that we have this Tg2 we have is equal to 120 degree Celsius and y2 is given as 0.03. So, from there we will be calculating in the same way we will be calculating Hg2 prime, that is equal to 1.005 plus 1.88 into 0.03 into 120 minus 0. Here also reference temperature is 0 degree Celsius plus 2500 into 0.03. So, it comes out as 202.4 kilojoule per kg. Similarly, this Tg3 is equal to 70 degree Celsius and y3 is equal to 0.05. So, from here we will be calculating Hg3 prime is equal to 1.005 plus 1.88 into 0.05 into 70 minus 0 plus 2500 into 0.05. So, that is coming out as 201.93 kilojoule per kg. So, we have now Hg1 prime, Hg2 prime and Hg3 prime. Now, we will be calculating this mass of the solid, and then from there actually we will be calculating we will be doing this we can say this one moisture balance and enthalpy balance. So, first of all we will be getting this mass of the solid, say LS. So, mass of the solid, that is we will be finding out this LS. So, LS is, it is given that the 30% is there, 30% moisture is there. So, the dry basis will be LS is equal to this 1000 into 1 minus 0.3. So, we can say this one, say that is 700 kg. Okay. Then whatever the xi will be, say out of this we can say this one moisture is 30%. So, this one will be, say we can say 1000 into 0.3 divided by 700. So, this is nothing but 0.429, and this x out, that is only 2%. So, we can say this one, that is the desired one. So, we can say 0.02 by 0.98. So, that will be like this 0.0204. So, we have this one x I and x out, and CPS also is given, that is supplied, the solid, that is 920 joule per kg Kelvin. So, this is nothing but 0.92 kilojoule per kg Kelvin. And say TSI is given, that in which temperature the solid is entering, TSI, that is we can say the entering at 27 degrees Celsius, and TS out also is given as 52 degrees Celsius. Okay. So, we will be calculating now the enthalpy of the solid. So, say we can say this one, we will be calculating this Hs in whatever the solid actually is entering with the enthalpy value, that is we can say this one Cps plus 4.187 into xi, that is into TSI minus say T0. So, it is coming out as, so we can say this one 0.92 plus 4.187 into 0.429 into this Ts in 27 degree Celsius minus 0 degree Celsius. So, it is coming out as 73.29 kilojoule per kg. Now, this whatever the enthalpy of the solid which will be leaving the dryer HSO prime, that is on the same way, but the moisture content is different. We will be calculating like this 0.92 plus 4.187 into 0.0204, that is the x out, into temperature is 52 minus 0. So, that enthalpy value will be like this 52.28 kilojoule per kg. Now, we need to do the moisture balance across this dryer. So, we can do this moisture balance across the dryer like this, that will be doing say like Ls into xi minus x out is equal to Gs into y3 minus y2. So, here actually Gs is equal to Gs2. So, this LS is equal to the 700 and Xi is equal to 0.429 and X out is equal to 0.0204. This is GS2 we do not know, but we know the moisture content of Y3 and Y2, that is we can say this one 0.05 minus 0.03. So, from here we will be getting this GS2, that is equal to, say we will be getting by manipulation we will be getting 14,301 kg. So, we can say this one dry air. Okay. So, now we need to do the moisture balance at the heater. We will be doing this moisture balance at the heater. That is just by doing the moisture balance, this GS1 into Y1 plus GS2 minus GS1 into Y3 is equal to GS2 into Y2. So, if we put all the values here, then we will be getting that GS1, that is not known actually. So, we will be putting this GS1 into Y1, we know this 1.018 plus GS2, just we have now found out this one 14,301 minus GS1 we need to find out into Y3 is equal to 0.05 is equal to GS2 is 14,301 into Y2 is equal to 0.03. So, from here we will be getting this, there GS1 actually GS1 is equal to, we will be getting that 8,938.2 say kg dry air. So, all this one as we have taken the basis as this 1 hour. So, it will be like that is also per hour, that is also we can kg dry air per hour, we can say this one per hour. Okay. Now, we will be doing this calculation like this, first flow rate of the fresh air, that actually is nothing but this one. So, we can say this one the first answer of this first problem, that is the flow rate of fresh air. So, that is flow rate of fresh air, that is we can say this one GS1, that is we have got this one as 8,938.2 kg dry air per hour. Okay. Now, we need to calculate that how much air actually is leaving the dryer, that is recycled. So, that is the second question, that how much leaving air actually we can say this one GS2 minus GS1, we can say this, that air leaving dryer that is recycled, that is we can say this one is equal to, say we can say this one GS2 minus GS1. So, it is say like this 14,301 minus 8,938.2, that is coming out to be as 5,362.8 kg dry air per hour. And then the question is that the fraction of the air that is from the dryer, that is fraction that is recycled, fraction of air this one from dryer that is recycled is equal to, we can say this one 5,362.8 divided by total, this one entry is 14,301, say into 100. So, that is coming out to be 37.5%. So, this is another this one answer. Now, we need to do the enthalpy balance over the heater. So, that is we can say this one, say for problem C, that we can say this one theoretical steam requirement. So, for that we can do the enthalpy balance over heater. So, there will be doing this GS 1 into Hg 1 prime plus that whatever is recycled back, that is a GS 2 minus GS 1 into Hg 3 prime plus which is lost actually. So, we can say this QH amount, that is nothing but we can say this one what is entering actually, that is say GS 1 into Hg 2 prime. Okay. So, we will be putting all this to get whatever the amount of heat is lost. So, that actually will find out from here. We will be putting this 8938.2 into this enthalpy value is 75.13 plus that is 14,301 minus 8938.2 into say 201.93 plus this QH we need to find out is equal to 14,301 into 202.4. So, from here actually after manipulation we will be getting QH is equal to 1.14 into 10 to the power 6 kilojoule per kg. So, this amount heat actually is lost, and we know this one, this latent heat, this lambda S actually is given for this one lambda S for at this 4 kg per centimeter square gauge pressure, that is given as 2110 kilojoule per kg. So, we can say this theoretical steam requirement is equal to, we can say this one from this basic formula QH by lambda S, we will be getting QH, we have got this one that 1.14 into 10 to the power 6 divided by 2110. So, from here we will be getting like this 540.3 kg per hour. So, that is we can see this theoretical steam requirement will be 540.3 kg per hour. Okay. Now, we will be getting how much heat is lost actually from the dryer, that we need to find out. Say we can say this one, we will be doing again the enthalpy balance over the dryer. So, suppose initially we have done the enthalpy balance over the heater, now we will be doing this enthalpy balance over this dryer. So, here we will be doing like this GS2 into Hg2 prime plus Ls into Hsi prime is equal to GS2 into Hg3 prime plus Ls into Hso prime plus this we can say this one how much load actually we are giving to this heater. Okay. So, all the values actually we will be getting like this that is 14301 into the Hg2 prime is 202.4 plus Ls is equal to 700 into Hsi prime is equal to 73.29 is equal to say GS2 is equal to 14,301 into Hg3 prime is equal to 201.93 plus Ls is equal to 700 into Hs out, that is we can say this one only 52.28 plus Qd. So, from here we can say this one Qd will be equal to 21,428.5 kilojoule per hour. So, we can say this one from the dryer heat loss is, so heat loss from the dryer is 21,428.5 kilojoule per hour. So, that way actually can calculate this performance of the continuous dryer. Now, we will be discussing on the rate of drying for continuous counter current dryer, and we will be calculating the drying time, and for that actually we will be dividing this, we can say, total dryer into so many segments. Like this, for the purpose of this mass and heat transfer calculations as well as for the calculation of the drying time, a continuous counter current dryer can be considered to consist of few zones. Like this, the zone, say for this simplicity, say we have taken that as 3 different zones are there in the continuous dryer. Say this first zone will be like this. So, that is we can say this one cold zone. So, where this we can say this one cold, we can say this one moist solid is entering with LS flow rate and with the moisture content is X1, with temperature is Ts1 and enthalpy as Hs1 prime. And this one, the hot air actually is entering from the this one from the zone 4. So, here you see this one, the stations are like this: station 1, station 2, station 3 and station 4. So, from station 4, the or we can say this one at the end of this zone 3, this we can say drying air is entering with the humidity with Y4 and temperature is Tg4 and enthalpy value is Hg4 prime. So, it is entering here, and in that zone actually where this hot air or drying air is entering, there we can say the whatever the temperature is applied to this drying solid, it is used to heat the drying solid at the desired temperature only. No drying actually takes place in this zone like this. So, that we will be discussing in detail. So, in the zone 1, say it is whenever it is entering in the beginning. So, the drying air which will be entering in the zone 1, with this we can say this one low temperature, because you see in zone 2 and 3 the hot air is used to separate the, we can say this moisture, and during this process the temperature is decreased. So, whenever it will be entering this zone 1 with this minimum temperature, we can say this one at Tg2. So, it is entering here and then it will come into contact with this, we can say this one wet solid like this. So, this wet solid temperature will go on increasing from Ts1 to Ts2 in zone 1, and this that we can see this one flow rate is Ls, and this moisture content actually will be definitely will be decreasing, that will be X2, that is we can see the critical moisture content, and then temperature will be increased from Ts1 to Ts2 and enthalpy also will go on increasing from Hs1 to Hs2. And then whenever it will be this one maintaining its critical moisture content, then you see temperature of the solid will remain constant. So, that is why from Ts2 to Ts3 the temperature is constant. So, we can say this one Ts2 is equal to Ts3, because at that condition the critical moisture content is already arrived. But at the same time, the whatever the drying gas which is entering at Tg4 at a high temperature, in this zone 3 we can say where only the heating of this solid takes place, that is decreasing its temperature from Tg4 to Tg3. Again in zone 2, this unbound moisture, we can say this one is removed, this bound moisture content up to critical moisture content will be the decreased from Tg3 to Tg2, and then in zone 1 this temperature of the gas will be decreasing from Tg2 to Tg1. So, we can say this one, this in zone 1, that is in this zone, or we can say this one in this zone, the same, this is called actually preheat zone. Solid is heated by the gas until the rate of the heat transfer to the solid is balanced by the heat requirement for evaporation of the moisture. So, we can say this is a preheat zone, and I discussed this also earlier that in this preheat zone the temperature of the drying gas is minimum, means when it enters its temperature was maximum, and when it enters the zone 1, that time its temperature is decreasing to a greater extent. And in zone 2, which is we can say this one just after this zone 1 and before this zone 3. So, it is we can say this equilibrium temperature of the solid remains constant, because while the surface and unbound moisture actually are evaporated, the critical moisture content Xc is reached at this boundary 3, or we can say this one critical moisture content actually now you see here this critical moisture content actually that here the critical moisture X3, or we can say this one whatever X4 also, both are same, means that is we can say critical moisture content, because you see after that the moisture is not removed from the system, only the temperature increases. From here you see temperature increases from TS3 to TS4, and then it is suppose the desired temperature, what is the desired temperature, based on that we can say this one where the station 4 will be, but you see the moisture content will not change. So, there dry patches actually appear on the surface, and unsaturated surface drying and evaporation of the bound moisture also occur. And zone 3 is nothing but this heated to the desired outlet temperature. Okay. Now, we will be this one doing systematic calculation of the drying time this for these 3 zones, but the convenient way of calculation is this: first we will be calculating this zone 3, then we will be calculating this zone 1, and finally, we will be calculating zone 2. Okay. So, for this we can say this one we need to find out the rate of heat transfer from the gas. This Q3 will be like this Gs into Ch into Tg4 minus Tg3. Then we have this heat transfer coefficient is equal to Ky into Ch, and this temperature driving force will be like this. This one we can say this one temperature driving force in the station 4, that is nothing but we can say Tg4 minus Ts4, and here temperature driving force in this we can say this one station 3 will be Tg3 minus Ts3. Okay. So, this we can say this one delta T4, this is delta T3. Now, as the temperature driving force is not linear or is not we can say uniform or is not same. So, that is why we need to get this log mean temperature driving force, that is simply we are getting delta T3 minus delta T4 by ln delta T3 by delta T4. And here actually you see time of heating, this how much time actually is required in the zone 3, that is we can say we will be getting by Q3 by SS into A prime into HC into delta T driving force, where this A prime is nothing but we can say this one effective surface area of the solid. So, that will be meter square per kg dry solid. Now, you see here TS3 and TG3 both are unknown. So, this in this case we can say this one both this TS3 and TG3 these are not known. We need to find out this TS3 and TG3, this one we will be doing this one. Now, we need to do the energy balance this one in this zone, that will be Gs into Hg4 prime minus Hg3 prime is equal to Ls into Hs4 prime minus Hs3 prime. So, humidity of the gas remains same over the zone, because we told that this Y3, Y4 all these are this one same, because after that no drying actually takes place, and TS3 is we can take this as the wet bulb temperature. Hence, we shall guess this TS3. Now, we can say this, we can say that is the wet bulb temperature, and then we will be calculating this Hg3 prime and then Tg3 prime, whether we are getting this wet bulb temperature is matching with this assumed TS3 or not. We need to find out this one. If it is matching, then our guess was correct. Now, you see this we will be doing the heat balance in the zone 1, because you see this one for convenience of the theoretical analysis we calculate the driving time for this zone, because before this zone 2, because the moisture content of the solid changes from X1 to Xc, then Y2 can be calculated from the moisture balance. Okay. Now, we know this one, this in this zone, because this is simply we can say this one, whatever the drying will take place up to, we can say this one, we can say critical moisture content, that will be N is equal to K y into Y s minus Y. That is nothing but, say we have already derived this one is equal to minus L s by L s into A prime into dx dt. So, and we know this one that for this type of this one system, if we take the slice also, we will be getting G s into dy is equal to L s into dx. So, we will be putting these two in this equation. If we put this in just after manipulation, if we put this and say in place of, we can say G s, or in case of this L s, if we put this one, say dt will be nothing but, this dt will be nothing but minus L s by L s into A prime, and so we will be integrating from 0 to T1 time, which is how much time actually T1 means, we can see this in the zone 1, how much time we will be taking this one, where the moisture content will be increasing from x1 to x2. Moisture content will be decreasing from x1 to x2. So, that is dx by n. This n will be replaced by this ky into ys minus y. So, we will be putting this n is equal to this yx ky into ys minus y, and then we can again do this one dx, we can keep this one in the form of dx, actually we can keep in the form of y also, gs by ls into dy, just we will be putting this one gs into dy by ls into ky, then this ls actually will be going. That is why we kept this ls from the beginning. So, ultimately what will happen, this after this integration we will be getting this gs into ky into ls into a prime into ln ys minus y2 by ys minus this y1. So, T1 will be like this, gs into ky into ls into a prime into a ys minus y2 by ys minus y1. So, this is the, we can say this one time requirement in, we can say this one zone 1. Okay. So, this is, we can say this one in the zone 1. So, now we will be calculating this one in the zone 2. Here actually we are assuming one this one our parameter like this, the moisture content of the solid is below Xc. If it reaches Xc, then we will not be able to calculate the we can say this one drying time in this zone, because after that nothing will happen, this only here also will be, what will be there will be no drying actually. That is why if the we can moisture content of the solid below Xc, then only we can say this one there will be some drying time. Okay. Here also we can say this in the same way, we can say this one, we assume here also this we assume that the drying rate is proportional to free moisture. Just here like this, if it is not proportional, if it is proportional to the square of the, we can say this one moisture content, then the expression will be to some extent different. Otherwise, it will be like this, we have already derived this, n is equal to n c into x minus x star by x c minus x star, that is after manipulation we will be getting ky into y s minus y into x minus x star by x c minus x star. Okay. So, for that case we will be getting this in the same way we will be getting t will be equal to L s by L s into a prime into x 3 to x 2 dx by n, and we will be putting this n, the formula this one n like this part we will be putting here in this, here we will be getting L s by L s into a prime into x 3 to x 2 dx into say this one x c minus x star by ky into y s minus y into x minus x star. So, just after manipulation and which are the constant parameters, we will be taking out this one from this entire expression L s by L s into a prime into x c minus x star from here and ky from here, then we will be getting this x 3 to x 2 dx by y s minus y this into x minus x star. Okay. Now, for this x actually we can say this one we need to do another thing, just we need to do one this one what is called moisture balance like this. For this zone G s into y s minus y 4, that is y 4 means that is also y 3 is equal to nothing but L s into x minus x 4. From there we will be getting x is equal to this one x 4 plus G s by L s into y s minus y 4. We will be putting this value actually in here, this in x we will be putting. Now, you see if the x star is 0, we can say this one, if the equilibrium y star content is negligible, means if it is 0, then this part will go, this we can say this one, this is 0 and this is also 0. Then we have this one for t2, just by integration we will be getting that x actually will be coming out here like this x part actually will be coming here like x 4 plus g s by L s into y s minus y 4, and we have this g s by L s into a prime into k y is there, and then this part is a dy by y s minus this y, like this will be that x c into y s minus y 3 by x 4 into y s minus y 2. So, from here actually we will be getting that say T 2 will be g s by g s into x c by L s into a prime into k y into x 4 plus g s by L s into y s minus y 4 and into ln x c into y s minus y 3 by x 4 into y s minus y 2. Okay. Now, actually we will be able to calculate the total drying time in the continuous dryer also, in this means in zone 1, zone 2, zone 3. So, in the next class we will be discussing on the drying time calculation from the drying rate curve. So, there we will be discussing different situations and we will be calculating the total drying time. Thank you.